Bruce kind of introduced my topic at the end of his last presentation. I'm just going to talk a bit about spectral reflectance. And I put all of these pictures and the different scales on my introductory slide just because there's lots of different scales that you can consider when measuring reflectance, everywhere from a single leaf measurement all the way up to satellite measurements of the Earth's surface. So I think mostly what I'm going to talk about is more reflectance principles, but we'll be down in more of this range of scale, but some of or most of what I will say will apply to all of the scales. And again, if you have any questions, feel free to ask while I'm going through the slides. Reflectance is a pretty simple concept. We just divide the reflected radiation, so everything that's bouncing off the surface and coming back, by the radiation that's incident on the surface. And it's powerful, simple but powerful, because we can learn a lot about surface properties, surface conditions, based on how the reflectance signal changes. We've already seen this plot more than one time today, so I won't spend too much time on it, but it shows the shortwave radiation spectrum at Earth's surface. And so in most applications, not all, because we can do this in the laboratory and we can also do it on small leaf samples where we often use artificial lights, but when we're talking about the scales of plant canopies and flux towers and things like that, typically the light surface or the light source is the sun, and so incident radiation is these data that you see right here. So then we have to invert our sensor and measure the reflected signal, and that goes in the numerator of our equation. And when we do that, it looks like this for some surfaces that we're all familiar with. I have water, soil, a plant canopy, and snow. And so you can see one thing that sticks out immediately from this slide is we can use reflectance to characterize what it is at the surface. I don't know that that's necessarily a major application because there's other ways of characterizing what's going on at the surface, but the reflectance signatures are very, very different when we move from one surface to the next. So this gives you an idea of how much it costs to measure the different wavelength ranges. So to get the visible spectrum and a little bit of the near infrared, maybe 350 or 400 nanometers up to about 1,000 nanometers or so is a reasonable price tag. Then to get that same wavelength range plus more of the near infrared, now we're talking about maybe half of the solar spectrum, we're getting a bigger price tag. And to get the whole spectrum, we're talking about a lot more money. And so the price scales with the amount of information that you're measuring. And I'm mostly going to talk about this range of 350 or 400 up into the 1,000 range, largely because that's the more affordable range, and that's the type of instruments that we typically deal with, at least at Apogee Instruments. So I want to focus on the reflectance spectrum for a plant canopy for a minute. You can see there are a lot of unique features here. One that we already talked about earlier is the photosynthetically active radiation range, which is 400 to 700 nanometers. The reason that it's so much lower than a lot of the other parts of the reflectance spectrum is because green leaves have a lot of chlorophyll in them, and the chlorophyll is absorbing all of the photosynthetic photons for photosynthesis. And so this whole portion of the spectrum is depressed, small values, because all of those photons are being absorbed for photosynthesis. And within that range we have this little green peak. We're all familiar with it. We can see it. That's why plants are green. There's the red edge, So the point where we transition from the photosynthetically active range to the near infrared range. It jumps up here because everything beyond about 700 are non-photosynthetic photons, so a high percentage of them are being reflected. And then all of these dips here are water absorption bands. So healthy plant leaves tend to have a lot of water in them, and once you get out into the near infrared range, water is a pretty good absorber of certain wavelengths. There's a water band about 970 or 980, another one around 11 to 1200, another one about 1400, and then another one about 1900 nanometers. And so we can learn something about, potentially about photosynthesis, about water, different variables based on measurements of plant reflectance. This slide illustrates how you would do it for a single leaf. So typically this is done in the laboratory and it requires an artificial light source. Here's a fiber optic cable that's going to absorb the light, take it back to a spectroradiometer, which actually makes the measurement. So when we start, we have to have a reflectance spectrum, a reference reflectance spectrum. We use a small, highly reflective white surface to give us a reference spectrum. Essentially, this would represent the denominator in the equation. When we make this measurement, this would represent all of the incident radiation, assuming our reflectance panel has a high reflectivity, something near 100%. And then, after we make our measurement on a reflectance panel, and often this is made out of Spectralon or PTFE, some material that has really high reflectivity, near 100%. Once we get our reference measurement, the denominator of the reflectance equation, then we can put the sample under the light source and measure the reflectance from the sample. And you'll notice we have to have some kind of flat black background behind the sample. Bruce talked a little bit ago about how reflectance and transmission spectra look very similar. They're kind of analogs of each other. Well, if you have some photons that are being transmitted through the leaf and you have a highly reflective background, like if we put the leaf over top of our reflectance panel, some of those transmitted photons would reflect off the white background, be transmitted back through the leaf, and actually get measured as reflected photons rather than photons that were transmitted all the way through the leaf, reflected off the back, and then transmitted back through the leaf. And so when you measure your sample, you put it on top of some kind of flat black background that has a very low reflectivity, so we can assume that all the reflection comes from the sample itself, in this case, a leaf. And so this measurement, as I mentioned, represents the denominator of our equation. This measurement over here represents the numerator of the equation. And so this is how you would make a laboratory measurement of a single leaf sample. And when we move to the field to do it for a plant canopy, for example, the actual method isn't that much different, and I'll explain it when we get there. So just to give you an idea of the kind of information that leaf reflectance might indicate, we have two reflectance spectra here. One where the peak in the green and then some of this radiation in the red is more reflected than the other. The reflectance is higher, I should say. This would represent a well-fertilized leaf with a high nitrogen content. This one would represent potential of nitrogen deficit. So you get changes in the spectrum as a function of properties of the leaf. Here it's related to nitrogen, but there could be other properties that we can measure by analyzing the changes in the reflectance spectrum. And so when we move to the field, The reflectance for a plant canopy looks similar to the reflectance of a single leaf. So the previous data were for a single leaf. This is actually a reflectance spectrum that we measured on a plant canopy. And in times past, we're interested in very specific portions of the spectrum. One that everybody I think is familiar with is the difference between red reflectance and near-infrared reflectance. So I highlighted them here. And for a long time, we've used reflectance measurements of these two wavelengths, somewhere in the red and somewhere in the near-infrared, to quantify NDVI. You've probably heard this acronym before. It's the Normalized Difference Vegetation Index, where we take near-infrared reflectance minus red reflectance in the numerator, and then we take the sum of the two in the denominator. Because we have strong absorption of photons and low reflection in the red and high reflection in the near-infrared, essentially NDVI is a greenness index. And we can measure it, and it tells us about how much leaf area is covering the surface, or how green the surface is. And there are small devices. This is an instrument from decagon devices that we can use to measure specific indices like NDVI. So this small sensor that I've shown here is essentially a two-channel or a two-band radiometer. It has one sensor in it that measures the red range and another sensor in it that measures the near-infrared range. It makes those measurements, does this calculation internally, and outputs an NDVI value. So if we're only interested in specific indices like NDVI, then small low-cost radiometers like this can be very useful. I showed some prices earlier of spectral radiometers, and $3,000 to $6,000 was a rough estimate of an instrument that would give you this reflectance spectrum. This two-channel radiometer is about an order of magnitude lower. This would be maybe a $300 instrument, somewhere in that ballpark. But red and near-infrared reflectance aren't the only wavelengths of interest. The red edge can be very informative. Often we're interested in blue reflectance. And there's another index, kind of like NDVI. The mathematical form is exactly the same. You'll see in just a second, that uses reflectance at 531 nanometers, a green wavelength, and reflectance at 570 nanometers, kind of a yellow wavelength. And it's called PRI. This means photochemical reflectance index. And so we take the reflectance at 570 and minus the reflectance at 531 and divide that by the sum of the two. And we get this PRI, and it's still being studied. There's a lot of work going on to better understand what PRI is actually measuring, but it seems to be closely related to light use efficiency of plants. And so PRI and NDVI we can measure again with these small low-cost devices like this, and I will say that Decagon also has a PRI instrument in addition to the NDVI instrument. And turns out there are a whole host of fairly simple reflectance indices that have been published in the literature. Here's a relatively recent review paper. This is actually a table from that paper, where 20 different, I think there's 20 of them on there, relatively simple reflectance indices are shown here that are all attempting to quantify different things. We've got chlorophyll content, photosynthetic activity, liquid water content, carotenoids and xanthophyll cycle, anthocyanin, canopy water content. There's lots of different plant properties that people have attempted to estimate using reflectance indices, or learn about using reflectance indices. I actually got a list from a colleague one time It's unpublished, but the list that she had compiled had 62 different reflectance indices in it. So there's a lot of these things out there. I guess the point that I want to make is if you're interested in one index, like just NDVI or just PRI, these relatively simple 2-band, and sometimes I've seen 3 or 4-band radiometers are available to give you information on a single index. But it makes sense that why not use the whole spectrum if we can, rather than trying to just build sensors for specific indexes only. And so that's what a spectroradiometer gives you, is a measurement of the entire spectrum. And one of the reasons I think that maybe this hasn't been more widely used, or is maybe just starting to be more and more applied in research, and especially in commercial operations, is in the past spectroradiometers have tended to be expensive. Oftentimes they're large and heavy, and so they require an operator or a computer, and so they're not necessarily easy instruments to take from the laboratory and use routinely in the field. It can be a little bit challenging. So hence there is a lot of use of these small narrowband single or dual or 3-channel radiometers. So the Apogee Spectroradiometer, we tried to design it to overcome some of these challenges and limitations, and make it more of a field instrument in addition to a lab instrument if you wanted to use it in the laboratory. So to give you an idea of the size, I actually have one. You can have a look at it. Some of the features are highlighted here, but really we wanted to try to make something low cost, small, lightweight, and that would interface with a data logger so that you could leave it in the field unattended, something that didn't require a person to operate it. And there it is compared to a couple quantum sensors, just so you can get an idea of the size. And so some applications, and I won't go into a ton of detail here, but this is the kind of thing that you could do with a unit like this. Continuous automated measurement of plant canopies. So often we're interested in plant response to environmental change, and this might be one way to quantify that, measuring reflectance spectra. And we can go now from having to have an operator in the field to collect data to potential connection to a data logger on a weather station or on a flux tower, or we can leave it in the field and make measurements over the space of an entire growing season or even an annual cycle, for example. Another potential application is precision agriculture, rapid field phenotyping of crop plants, looking for differences in genetic lines or differences in different treatments. We can mount them on mobile instruments and collect high frequency data for precision ag. And so I said a few minutes ago when I was explaining how to make the reflectance measurement in the lab that the procedure was relatively similar for making measurements in the field. Well, so there's a couple of different approaches that you can take. One would be to mount one instrument level and looking up, and another instrument pointing down at the plant canopies. So this gives you the reflected spectrum, this gives you the incoming spectrum. The ratio of the two is a reflectance measurement. Using an approach like this, you actually have to match the spectroradiometer. So in essence, it's a field calibration. We want the data for this one to match this one when we have 100% reflectance. So what that means is you have to use a reflectance panel, which is a diffuse reflector with reflectance near 100% to match the spectroradiometers. And so before you start, it essentially means you have to put your reference panel, your reflectance panel, underneath the downward looking instrument and then calibrate this one to match the output from that one. And then when you remove the reflectance panel, you can take the ratio directly and it will be a measurement of reflectance. And so there is some, as you say, requirements of users being in the field to make the system work before you start. We have to match the spectroradiometers. Another option is you could make measurements with a single downward looking instrument. So if we take this one away, we can make measurements with this one by saving the measurement when we've got a reflectance panel here. This becomes the denominator in our equation, and then when we remove the reflectance panel, subsequent measurements become the numerator in the equation, and we just take the ratio of the two. The challenge with doing it this way is every time the sky conditions change, we have to make a new measurement of the background radiation with the reflectance panel. Because if the sky conditions change, that means the denominator in the reflectance equation changed, and we have to account for that. So there's multiple ways to do it. Using two instruments like this would be the way to do it for long-term unattended measurements. If you only had a single measurement, that'd be the way to do it. If it's more of an on-the-fly mobile measurement where it's convenient to make the reflectance measurement, the background measurement, periodically as the sky conditions change. So we actually made some measurements. We're still in the process of beta testing and this instrument. We actually made some measurements in the backyard of our facility at Apogee Instruments in Logan, Utah, just over a turf grass surface. So our configuration essentially looks like this. We have an upward facing instrument and a downward facing instrument. We used a Spectralon panel to match the downward instrument to the upward instrument. And this gives you some sample data. As I mentioned, this was over turf grass. To make it a bit more interesting, we intentionally stopped irrigating the turf grass. So this is the reflectance measurement on the last day that the irrigation system was on. And then we turned off the water. About 3 days later, on August 24th, the reflectance spectrum was here. 5 days later, on August 29th, it was here. And then 4 days later, on September 2nd, it was here. And so you can see there's some pretty substantial changes in the reflectance spectrum as the grass dries out, going from well-watered to water-stressed. This is the kind of data that spectroradiometers yield. The changes in or plant responses to environmental change. And we can potentially learn a lot about plants without having to sample them and take them back to the lab for analysis, because now we have a way to measure the light reflectance as a function of changes in the environment. That's all I have. I want to leave plenty of time for Bruce to cover oxygen.